The sea east of Japan trembled again, a deep, resonant pulse that rippled through the Pacific margin and sent instruments across the nation flickering to life. Beneath those cold waters, where the Pacific plate grinds relentlessly beneath Honshu, 3 strong earthquakes struck in quick succession. Magnitude 6.8, 6.4 and 6.0. Each rupture tore along a fault that has been straining for decades, releasing bursts of energy like cracks in a vast, invisible dam. Are these tremors a warning light blinking on and off, or simply the Earth rehearsing another ordinary day on a hyperactive boundary? What do rapid clusters like this tell us about the stresses locked and loaded beneath northeastern Japan? And how closely do such sequences echo the preludes to the great disasters of the past? On the morning of November 9th, 2025, Coordinated Universal Time, a shallow undersea shock of magnitude 6.8 ruptured a patch of the Japan Trench, roughly 126 kilometers east of Yamada, Iwate Prefecture, centered near 39.396 degrees north and 143.411 degrees east at an estimated depth of 10 kilometers, about 6 miles. Less than an hour later, a second shock of magnitude 6.4 broke nearby, followed within a day by a third of magnitude 6.0. Dozens more small and moderate events clustered through the same hours and days. For anyone who remembers the seismic choreography that culminated in the magnitude 9.0 Tohoku rupture in 2011, the pattern is eerily familiar. Yet familiarity is not the same as causation, and the geology underneath northeastern Honshu resists simple narratives. To understand what happened and what these events reveal about the mechanics of subduction requires stepping inside the physics of the plate interface. The locked asperities and creeping patches, the redistribution of static stress and the passing of dynamic waves, the role of fluids and slow slip, and the way rupture nucleates and propagates on a heterogeneous megathrust. Japan sits astride one of the planet's most vigorous convergent margins. Here, the Pacific plate dives beneath the overriding Okhotsk microplate, commonly treated as part of the broader North American plate in tectonic syntheses along the Japan Trench. The convergence is not slow. Rates in the northeastern sector cluster around 80 to 90 millimeters per year, about 3 to 3.5 inches per year, a pace more than a handful of coins stacking up each century. Such persistent motion imposes shear and compressive stress on the plate interface, and where patches of the interface are locked by friction, these stresses build until failure. That failure can take many shapes. A patch may break in a single fast slip, producing a conventional earthquake and energetic seismic waves, or it may fail by slow, aseismic slip that leaves only subtle deformation recorded by geodetic instruments. Or it may be the prelude to a rupture cascade that ultimately roars across a much larger portion of the interface. The recent sequence in early November 2025 comprised shallow shocks, all roughly 10 to 11 kilometers deep, about 6 to 7 miles, a depth range consistent with interplate thrusting on the megathrust or failure within the near-surface portion of the subducting slab. Shallow depths matter enormously. Ruptures close to the free surface couple efficiently to the ocean and the crust, generating strong ground motions and amplifying risks to coastal communities. They are also the kinds of slips that plausibly interact with adjacent locked patches through static Coulomb stress changes. In crude terms, when a patch slips and releases stress, some surrounding areas feel increased shear stress and are pushed closer to failure, while others are relieved. That redistribution is not uniform. It depends on the geometry of slip, the orientation of nearby faults, and the elastic properties of the crust. A typical scenario for a clustered sequence is this. An initial rupture releases enough local stress to produce significant elastic loading on an adjacent patch, nudging it toward failure. That adjacent patch slips in turn, and the chain continues until a sufficient volume of the interface has released its accumulated strain. The time scale of such cascades can be seconds, minutes, hours, or days. The November sequence was temporally compact. The magnitude 6.8 event occurred. Then, within the hour, a magnitude 6.4 followed, and within a day, another magnitude 6. Within the seismological literature, such quick successions are often described as earthquake clustering or sequences of interacting ruptures. They imply that the regional stress field was close to a critical threshold in multiple nearby patches. The initial rupture served as a trigger by perturbing a delicately balanced system. But triggering is not the whole story. The mechanics of rupture initiation and propagation are governed by rate and state friction laws, which capture how fault resistance evolves with sliding rate and contact state. These laws explain why faults with identical static stress may behave differently depending on their recent slip history. A fault patch previously unloaded by aseismic creep may behave more stably, radiating little seismic energy, whereas a tightly locked asperity with high-strength contrast may produce a large, abrupt slip. The heterogeneity of the plate interface, patches of high coupling interleaved with creeping zones or pockets of elevated pore fluid pressure, sets the stage for complex rupture geometries. In northeastern Honshu, seismic imaging and earthquake catalogues over decades have revealed a patchwork. Some segments of the megathrust are strongly coupled and capable of storing large elastic strain, while others slip more readily in slow slip events or tremor. Foreshock sequences, like the one observed prior to the magnitude 9.0 Tohoku earthquake in March 2011, complicate the search for a universal trigger. In that earlier crisis, a magnitude 7.3 event struck on March 9th, followed by other moderate shocks, and then on March 11th, the gigantic rupture began. Studies of those days have offered mixed interpretations. Some researchers detected a small transient slip beginning roughly 2 days prior, while others argued that the observed geodetic signals were consistent with afterslip following the foreshocks rather than true precursory slow slip. The key point from those analyses is that the foreshock activity and subtle deformation did not form a simple monotonic acceleration unmistakably heralding the megathrust. Instead, they expose the messy physics of a heterogeneous interface where a variety of processes, seismic and aseismic, interplay. Applying that lesson to the November 2025 cluster, geoscientists will look first to the kinematics of each event, focal mechanisms, the spatial pattern of slip, and the orientation of rupture. Thrust mechanisms aligned with the trench would argue for classic megathrust rupturing, whereas significant non-thrust components might implicate splay faults in the upper plate or normal faulting within the subducting slab. The shallow depths and epicentral locations east of Yamada favour a megathrust interpretation, but only careful inversion of seismic waveforms and geodetic data can resolve how much of the slip occurred on the interface versus nearby structures. Seismic waveforms themselves carry fine-grained information. High-frequency components betray abrupt slip on small asperities, whereas low-frequency energy can indicate slower, more distributed rupture. Analysis of the spectrum of radiated energy combined with moment tensor and finite fault modeling can reveal whether the magnitude 6.8 event was a compact rupture or a composite of several sub-events. If the initial rupture was complex, with multiple sub-patches slipping asynchronously, it might have produced a more effective Coulomb loading of neighbouring sections than a simple, uniform slip would have. Conversely, if most of the slip was shallow and limited in areal extent, its capacity to trigger further rupturing on a distant, strongly coupled section would be limited. Beyond static stress transfer, dynamic stress changes, the fleeting but powerful shaking as seismic waves race through the crust, can also trigger earthquakes at sites remote from the initial rupture. Dynamic triggering is observed in many settings. Passing seismic waves can alter pore pressures, unclamp faults, and incite failure on critically stressed patches. In the immediate neighbourhood of a large quake, dynamic stresses may be large enough to spark aftershocks within seconds to minutes. Over longer distances, dynamic triggering can still catalyse microseismicity or promote the onset of slow slip. In the November sequence, the close time spacing suggests both static Coulomb transfer and dynamic effects likely contribute to the cascade. Fluids embedded in the megathrust system add another layer of nuance. The subducting oceanic crust carries sediments and volatiles that release water as pressure and temperature rise during descent. Elevated pore fluid pressures reduce normal stress on fault planes and can dramatically lower the effective frictional resistance to slip. Regions of overpressured fluids are often associated with seismic tremor and slow slip, and they can localize fault weakening. If the November ruptures intersected areas with high pore pressures, even modest increases in shear stress from a neighbouring slip could result in seismic failure. Conversely, if fluids drained or migrated away, adjacent patches might have been hardened, resisting triggered failure. Fluid pathways, permeability contrasts, and the history of fluid migration are therefore central to interpreting sequences. Another process of interest is afterslip, which is aseismic sliding that decays following a seismic event. Afterslip redistributes stress and can both promote and inhibit subsequent earthquakes. It tends to occur on the periphery of seismic ruptures, where frictional properties favour stable sliding. In some case studies, afterslip following moderate quakes has triggered additional shallow seismicity. In others, afterslip has relieved stress enough to dampen the aftershock rate. For the recent cluster, discerning the balance between seismic aftershocks and aseismic afterslip will require precise geodetic records. Continuous GPS measurements can capture millimetre to centimetre scale deformation, revealing whether the adjacent interface is slipping quietly or producing a sequence of small seismic ruptures. Rupture segmentation is another critical concept. Megathrusts are rarely uniform. They are made up of segments separated by zones of differing coupling, geometry, or sediment thickness. Large earthquakes often stop at segment boundaries, but sometimes they can jump across them. Whether a rupture propagates depends on the available elastic energy, the frictional resistance ahead of the crack tip, and the contrast in strength across the boundary. The magnitude 9.0 Tohoku event ruptured an unusually long portion of the trench, partly because a chain of strongly coupled patches gave way nearly simultaneously, and local geometrical features did not halt the propagation. In the November sequence, the observed organization of slip, whether confined to a narrow strip or spanning several segments, will be decisive in judging the potential for linkage to larger segments. Seismologists also study foreshock statistics more generally. Across global earthquake catalogues, foreshocks precede some, but far from all large earthquakes. When foreshock sequences do occur, their spatial temporal patterns are highly variable. Some display migration toward the eventual main shock epicenter, suggesting progressive weakening. Others are scattered and intermittent. Attempts to extract robust precursory signals from noise have largely failed to produce reliable, predictive diagnostics. Instead, the best that can be said is probabilistic. The occurrence of a sequence of moderate shocks increases the immediate short-term probability of additional earthquakes nearby relative to background. But it does not provide deterministic foresight. That probabilistic framing carries practical implications for hazard assessment. Operational centres can and do issue short-term forecasts that quantify aftershock probabilities, employing empirically derived models such as the epidemic-type aftershock sequence formulation. These models use the observed magnitudes, times and locations of initial events to estimate the likelihood of future shocks of various sizes within a given space-time window. Such forecasts are not predictions of a particular large quake, but they are grounded in statistical regularities of seismicity and can guide preparedness actions. In the context of the November sequence, the immediate forecast would focus on elevated probabilities of additional magnitude 5 and magnitude 6 range aftershocks in the coming days to weeks in the rupture zone and its periphery. Finally, an examination of the geologic record provides essential perspective. The Japan Trench has been the locus of repeated great earthquakes over centuries and millennia. Paleoseismology and tsunami deposit studies show that very large ruptures recur irregularly, sometimes separated by centuries. The mechanisms that produce those infrequent giants are the same ones at work in the November sequence: frictional failure on the plate interface, stress accumulation due to plate convergence, and the modulation of failure by fluids, heterogeneity, and transient slip. What differentiates a modest cluster from a great rupture is mainly the size of the coherently slipping region and the balance between energy release and frictional resistance across that region. In the immediate aftermath of the November events, the scientific imperative is clear. Integrate high-resolution seismic waveform inversions, continuous geodetic time series, and regional seismicity catalogues to resolve the geometry and kinematics of rupture. Are these events concentrated on a narrow trench parallel strip? Do they link up with deeper, strongly coupled patches that could host a larger rupture? Is there evidence of accelerated aseismic slip? Or do the data favour a sequence of discrete seismic failures driven by elastic interactions? Answering these questions will not yield predictions, but it will elucidate how the crust accommodated the recent strain release and how stress has been redistributed across neighbouring portions of the megathrust. In the end, the Earth's mechanics are stubbornly complex. The magnitudes of the recent quakes, magnitude 6.8, 6.4 and 6.0, are large enough to command attention and to perturb the near-field stress environment, yet they are modest compared to the giant failures that occasionally sweep hundreds of kilometres of the trench. They are, however, the very kinds of ruptures that illuminate the physical processes at the interface. How asperities break, how slip transitions from brittle to stable, and how fluids and geometry modulate failure. Through careful seismic and geodetic forensics, we will learn whether this cluster is a self-contained burst of activity or a sequence that has altered the readiness of adjacent segments. For now, the data speak to a dynamic interacting system where failure in one place begets change in others, where static and dynamic forces mingle with fluid pressure and frictional memory, and where the restless plate boundary continues to write its story in slips both silent and violent. If you found this deep dive into Japan's seismic activity fascinating, don't keep it to yourself. Smash that like button, share it with your friends, and subscribe to stay ahead on all things earth-shaking. And don't forget to tap that hype icon. Every tap helps push this video to a wider audience, so more people can explore the power and mystery of our restless planet.